Very much for coming. It is my great pleasure to introduce Professor Ravi Duddu today to give our beloved CPEP seminar. Ravi, we learned yesterday, went through quite the hazing experience to be accepted to the prestigious institute of the IIT Madras for his undergrad, and then came to the US to do a PhD at Northwestern, research stints at UT Austin and Columbia, and has been at Vanderbilt since 2012, and is a master of modeling the fracture and other degradation of materials with a recent-ish focus on ice. How recent? How long have you been working on it?
I started in my second postdoc 20 years.
Okay.
Yeah.
Not that recent. Long-standing expert in ice fracturing.
More than a decade.
In more than a decade, yes. So I think that's all the misinformation I'm going to spread. And from here on, it's my great pleasure. Thank you, Ravi, and please take it.
Thank you. Thanks, everyone. Thank you, Phil, for hosting me. And the weather's been great. I've had a great trip here. And so I'll get started. And hopefully I won't go over time. I'll try to keep it to 45 minutes. And I want to share some computational modeling studies that we did on how glaciers flow and fracture, how they deform. And the emphasis always has been that how do we introduce data? And it's always that people who collect data have a lot of data, and the modelers, oftentimes we don't know what to use them for. And then modeling gives a lot of information which sometimes don't necessarily understand, don't necessarily address what observations are shown. So there's this tension between observational, experimental people and computation. So I always try to bring them together in my work. And I want show a few where we were able to do that and maybe get some feedback and suggestions from you all. So before that, let me acknowledge that all this work wouldn't have been possible without my PhD students. Most of them were at Vanderbilt, one was at Imperial College, and then most of the postdocs, I didn't have to fund them. They just collaborated with me through the funding they were able to obtain through fellowships and all. So grateful for that, and then contributions from co-PIs. I didn't want to put names. I'd like to put faces on being a very visual person and so forth. So maybe some of them you already know through your personal contacts, and all the funding agencies for their support. So this is how I'll start with a high-level introduction where the motivation lies, and then 3 examples. One would be these water-filled crevasses, where water sits in them and then fractures propagate, and we use this model or method called phase field fracture. So I'll go through brief details on it. Then I'll switch to another type of flow fracture model that we recently worked on for hydraulic fracture, where there is turbulent fluid flow in the fractures that drives these in Greenland. And then a very large-scale rift propagation in shallow ice shelves. And there it's more like a method development exercise, and then we'll show how it applies to Larsen C, where we switch to something of a primitive model called continuum damage model that is related to phase field fracture in some way. And then I'll try to conclude. And I'll keep the equations brief, just show most of the simulation side. And usually when I give this talk in more of an engineering type discipline, I have to tell them what ice sheets are. I don't have to mention much to this audience, but that's Greenland, that's Antarctica, and that's our planet. And the quick takeaway point is that they are huge sources of fresh water. They contain enough water to raise the sea levels by 65 meters. If they disappeared for some reason, that makes good Hollywood movies, I guess, like the Doomsday. But thankfully, most of that water doesn't go away anytime soon. But the takeaway point is, even if we had 1 or 2% loss, that's still a meter or more of sea level rise. And the question is, what does that do to the coastlines and other regions which are low-lying, right? And that's always been the big societal level question for ice sheet modelers. And then going a little bit deeper into this, where we look at an ice sheet itself, you have a grounded portion that we typically can call ice sheet, and then the floating part where ice becomes buoyant and also starts flowing faster, so it starts thinning. It's called the ice shelf. And then on the top of the ice, sometimes during warming periods, you can have meltwater that forms lakes, and then it flows into cracks. And that's when we have water-filled crevasses. And these water-filled crevasses can have hydrofracture in a quasi-static sense, or also in the dynamic sense that happens on supraglacial lake drainage events. And eventually these fractures produce icebergs, which we call iceberg calving. And sometimes the fractures are also under the ice shelf, which are basal crevasses, which I won't be explicitly modeling, and we'll use some parameterizations for it later on. But this is sort of the setup from a mechanics point of view that we are looking at. And we primarily focused on ice shelves for the large-scale models, but then when we talk about small glaciers, we're looking at surface crevasses in the grounded portions, which are fast-flowing. Now, the high level again is fracture in ice sheets is a major contributor to sea level rise, and the frequency of calving events is increasing. In the ice shelves, while ice shelves don't directly contribute to sea level rise, you can have a speed up of the land ice behind the ice shelf, and that could cause more contribution to sea level. Based on what the literature says, Greenland could contribute maybe a few centimeters of sea level rise by 2100. Antarctica is largely uncertain. It could be just a couple of tens of centimeters, or it could be as much as 2 meters. And that's where a lot of the uncertainty that we have comes from fracture. Right? So only if we understand these fracture processes better and parameterize them in ice sheet models, we could start to understand, is it really 20 centimeters or is it 2 meters or more sea level profile. So that's another big societal level science question, I would say. And it's kind of ironic. I saw this article last month. I went to give a talk at King Abdullah University of Science and Technology. It's in Saudi Arabia, and they are, as you know, a completely oil-based economy. And they were saying like how it's ironic that most of these ports all around the world, which do serve as major oil ports, they are under severe risk from 1 meter sea level rise. So even if you are an oil trader, you have an interest in understanding sea level rise and how to protect themselves against this, which is inevitable, right? Like if you're talking about 1 meter sea level rise, it's not a question of whether, but it's a question of when it will happen and how soon and what do we need to plan for, right? And so I had much less resistance in Saudi Arabia and Abu Dhabi on sea level rise and climate change than oftentimes we hear in the United States. So that tells you something. And this is some website where they talk about long-term consequences. So New York is kind of in a bad situation. Even with the current 1.5 degrees global warming, you're seeing a lot of inundation near the Statue of Liberty. If you go to 3 degrees, then it's going to be some more. But if you look at some place like Dubai, right, where I was after at NYU Abu Dhabi, and there, if you did cut the emissions, then you're looking at a situation where there is not much inundation as opposed to 3 degree global temperature rise, where you are seeing a lot of inundation, right? And so, especially for these oil-rich countries, it's a real issue, and they are taking it a lot more seriously, I would say, with this study. Okay, so big picture now. Let me come down a bit more to the fracture side. I'm a civil engineer who studies fracture in materials, and I was intrigued by this very phenomenon of how widely different calving behaviors are across different ice shelves. So if you took, for example, Larsen B ice shelf, which is an Antarctic peninsula, then it in 2002 to 2003 went through a very fast disintegration process that's termed as explosive disintegration in this review paper that Jeremy Bass wrote, and I was a contributor to it. And there, the ice shelf had some meltwater, there was a warming period, apparently there was hydrofracture, and then the whole ice shelf kind of disintegrated in a matter of months. And then it refroze and became fast ice, and so what you're seeing here is sort of like that fast ice that kind of refroze, but it went through this sudden disintegration into very small icebergs and broke open. But whereas if you look at Thwaites Glacier, which is often called the Doomsday Glacier, I don't know whether it's really doomsday or not, but it still exhibits a lot of sustained iceberg calving. So you have fractures that form and then they break up, you have icebergs, and you get these small sustained calving events. And then on the other side, if you go to something like a Brunt ice shelf, there you get these really large rifts, and you can see the size scale here, tens of kilometers long, and you get tabular icebergs that are as big as the size of Manhattan or state of Delaware even. And then like these icebergs get transported, they change ocean circulation and all, and that's what I believe Till you're an expert on. So I look at iceberg formation, and then you study how then the icebergs evolve in the ocean system. And so it's and why does it happen in these wide length scales? And can we have one model that explains all of these when deployed at different scales, right? These are all continuum scales, so maybe there is one continuum model that does it all, right? And so that has been the objective that I've always been pursuing. So you have classifications in glaciers and ice shelves where you have these vertical cracks, which are often called crevasses. And then you have these very large in-plane fractures in ice shelves that people call rifts. And they almost use the terms as if crevasses and rifts are not interconnected and they're separate entities. But truly, if you see, it's a fracture propagation. It's a 3D fracture in a sense, where when the fractures propagate from the top of the ice and they reach the bottom, then they form a full depth fracture, and then when they start propagating in the length direction, they become a rift. So we need a unified three-dimensional model that can then also account for the fact that ice is a creeping solid. So it has this special type of time-dependent deformation that comes into play. And it also is related to the prior material state, and then it's a time-dependent evolution problem. So if we try to model that together, maybe we can describe all of these phenomena in one single frame, right? So with that as the objective, let me first look at the crevasse propagation. And in there, we started with questions. Okay, as an engineer, I'm always used to like, hey, I have a hammer, provide me with a nail, right? Sort of like in the layman point of view. But it is always important to say that I have a tool, what is the problem that it can solve? What is the science question that it can really solve? And in this case, the question that we addressed was, can hydrofracture, that means when you have cracks like this, surface water, meltwater goes into these cracks, can it drive these cracks all the way down, full depth? And this is not a new question. It has been addressed in various different ways and using analytical methods, a few decades ago. But we wanted to look at it in this new 3D unified phase field fracture formulation. And then the question that has not been addressed is, how does crevasse spacing influence these crevasse depths in glaciers and also crevasse patterns, right? So that's the new question that we also said now we will be able to address. So let's see how we set up the model. So the phase field framework goes back to this energy-based approach for fracture that was proposed in the 1920s by Griffith. And it's a diffuse interface approach to fracture. That means, let's say you have a body and you have a crack. Typically you interpret that crack as like, sharp interface that is separating the body into two pieces, correct? But in the phase field, what you're doing is you're not representing it as two surfaces, because then you have to do a lot of algorithmic changes to represent those two surfaces. But instead what you're saying is, let's call that a damage zone, and let's define an implicit function, a phase field function, which is a scalar function, that tells me that wherever that phase field is 1, let's say, that is corresponding to the fracture, and wherever it's 0, that means it corresponds to the body, where there are no fractures, right? So by simply tracking the value, the scalar value of this field at every point in the domain, I can say where the fracture is and where the fracture is not. So it's in a way, it's sort of like a level set type approach, if that makes sense, right? And now what that does is it allows us to write the energy, the potential energy in the body, where some of the contribution comes from the elastic strain energy, some of the contribution comes from the energy that is required to open up cracks, and then some of the energy comes from the external work done by the body force. Because in all of these problems, in glaciers and earth science, the driving stress is essentially the self-weight of the material. Whereas in, say, composites or some other lab experiments Natasha, right? Yeah, so you do, it's mainly external applied forces, right? But in a real glacier system, there is only gravity that is driving all the deformation, flow, and fracture. So we have to have the term, body force term, and then you use degradation functions, these quadratic functions, to basically say that when d is equal to 1, the material is damaged there, so it should not have any elastic strain energy. But when d is equal to 0, there is no crack, so the GC, the crack part, should have no energy, right? So you're basically writing a phase-based function for the energy, and then when you minimize it, the idea here is that a body will always try to minimize energy and then go to some kind of a quasi-stable state. And so when you minimize this energy with respect to two variables, the displacement corresponding to the deformation and the damage corresponding to the fracture field, you get two equations. And one of those equations is familiar to most mechanicians, which is just your equilibrium equation. We do some more work to introduce the fact that there's also fracture, water pressure in the fracture, so we incorporate the Terzaghis principle from soil mechanics to incorporate fluid pressure within fractures. I won't go through all the math details on that. And then we have the body force term, so that's equilibrium. That gives us the stress state, and that stress state defines something called a crack driving force that tells us how the fracture will propagate. And the fracture equation itself is essentially a Poisson equation. So there is a Laplacian term, there's a length scale that tells us how wide those fractures are. And then the crack driving force tells us how the stress is driving the crack tip to propagate into new fractures. And so this was the first paper that we know of that we wrote from our group with using the phase field fracture model for ice and glacier problems, right? And so then we did some more additional studies. So I'll skip, all the method development and the model development aspects to just go to the results straight. So let's look at a simple idealized case where there is a rectangular glacier and we have a small fracture initially at somewhere in midspan, and then we put a little bit of water in that crack to pressurize those fractures, and then it's in contact with an ocean that is providing some kind of compressive stress. Right? So this is an idealized problem setup that Jeremy Basis and I came up with in our first paper that published in GRL, Geophysical Research Letters, and in 2012, right? So this was the idealized case we made up. And in that case, the fracture is going to propagate vertically, and you're going to get some depth depending on how high the ocean water is, and how much water there is in the crevasse, right? And so for that kind of simple case, you have an analytical solution. I have a whole slide with all the equations of the analytical solution, but I just removed it in the interest of time. I can show to anyone who's interested in looking at the details, but the lines are the analytical solution for 3 different cases where there is no water height. That means it's sort of like a land terminating glacier, not in contact with water. If the water height is 50%, then you get this red line. And if the water is fully there at 90%, that's near flotation, related to the density of water being 90% of the density of seawater, right? So the density of ice is 90% of density of seawater. And beyond that, the glacier becomes floating. So you can never have more water level than that. And so we get these analytical solutions, and then for each of those cases, for a different water height in the crack, we run phase field simulation. That means each of these points is a phase field simulation that we ran. And then you see how it perfectly matches with this analytical solution. So that's when we said that, okay, first of all, this verifies that the phase field model that we set up actually works. And then it also shows us an interesting behavior that when your glacier is near flotation, you really don't get any fractures more than 8% of the glacier height. That means if you have a 100-meter thick glacier, you only have cracks that are 8 meters deep. You would never get more deeper than that. Right? So then, why does calving occur? So one of our studies conclusions here is that it must be basal crevasses that are actually causing some of these fractures, or there is some kind of undercutting, and then it actually becomes a fully floating, and there are other mechanisms that are playing to go forward. But that said, this study only looked at matching the analytical model with the simulation to benchmark it. And we generally find that filling crevasses with water makes them propagate to greater depths. So that's why as you fill more water, the depth of the crevasses increases. And seawater also suppresses fractures. So simple idea there. And then when we did multiple crevasses, what we expected is that the system would go towards so-called high depth, if that makes sense to some of the glaciologists here. That means you have many cracks, they start shielding each other, and so they would overall propagate to a lesser depth. And for that also, you have an analytical solution, and you can set up these simulations, and then you get pretty good matching with those cases as well. So that was more of a verification exercise, and then we started looking at some more advanced simulation setup. Okay? And so we formulated, to go to 3D, we formulated all this work before we did in COMSOL in 2D. So whatever I showed in the previous 2 slides was COMSOL. And first, we didn't want to pay for licenses. It was expensive. And second, it was still very slow. We would have convergence issues and all that. And so we created the software for phase field implementation of crack evolution, named it SPICE. Of course, being a fan of the Dune movies and also being Indian who likes spicy food, likes spice a lot. And it is a fully parallel, automated differentiation capable finite element code that's in Python. And all you have to do is define the so-called weak form, if any finite element weaks out there, and it'll do the rest for you, right? And so we set this up, and it's all open source, by the way. And we have 2 cases where I will first show the case where maybe I have to run this manually. So if you set up these initial cracks wide apart, then you have the 3D fractures, which are crevasses in the vertical, but drifts in, maybe you can call them drifts in the horizontal, and they're growing like isolated, straight, so-called drifts, if I may call them that. But they're still crevasses because they're not that wide. So this width is 750 meters, so that means it's almost a kilometer, and this one is 1.5 kilometers long. So that, and the fractures are resolved with the length scale, the phase field length scale of 10 meters approximately. Right? So still very intensive simulations. So we have to use maybe tens of millions of unknowns to solve this. So this one probably had close to 20 million degrees of freedom at the end of the simulation, right? And then if you do the same thing with much closer crevasse spacing, which means you have some crevasses that propagate fully, form drift, some just stop somewhere early, some will go farther but then fail to connect. You also see crevasse interaction where, in certain regions the crevasses are curving, and you get this sort of crevasse field, which looks realistic. And Luke, maybe you went to a field site and you saw some of those kinds of closely spaced crevasses. And what we show through this is that, yes, in fact, there is this influence that comes out where it can prevent not just crevasses from propagating to a certain depth, but also they change this interaction if they're closely spaced, right? And then we proceeded forward to set up more simulations where we want to look at these boundary condition effects. So in the previous case, the lateral margins were just free. That means they were freely sliding. But now I have the same domain, but I'm fixing the back surface and keeping this one free slip on the front surface, right? And then I want to see how the fractures will evolve, and the ice is here at the grounding line or fixed, whereas this is the terminus where it's open and going. So the ice is flowing from left to right, okay? And if I set that up, and then let me run the simulation again. Let run this movie. And what we see is immediately, almost instantly, I have damage in that fixed zone. Okay? And maybe this is the so-called shear margin or whatever, where as it's, and this is the center line, right, where the ice is flowing faster. It's a symmetric boundary condition. And so you almost immediately have to damage that point where it is connecting to the lateral fixed edge. And then your cracks in the middle will start curving, and you only see fractures near the terminus, you don't see anything behind. And this sort of tells you maybe in this stress state, calving happens only in this region, and also the frontmost crack doesn't even propagate because it goes into this compressive arch-like region, even if you didn't have the bending coming from the ocean water pressure in the ice shelf. So this is not an ice shelf. This is still grounded but free slip, right? So if you add bending to it, it might change it even more further, and if you have basal crevasses, that could change the dynamics also more. But you see these interesting curved crevasses, right? And then we said, what if for some reason this fixed boundary became free slip? Maybe the fractures went full depth and the glacier slid. And so what happens then, given this as the initial condition, right? Remember, our idea was that unified fracture framework, we not only capture the flow deformation of ice, but also maybe some kind of initial damage state effects. So I take this simulation endpoint and then change the behind the back face to a free slip, and then I look at it, I get these polygonal fracture patterns that just rip through the rest of the domain, right? That means that if you are, I don't know if this is realistic or not, but what we see is that these fractures can only form when something happens to this margin and actually becomes like a free-flowing, such that there is enough stress in here, and then you have crack branching and all that automatically comes through, even if we didn't put any initial heterogeneity. It's all homogeneous ice, but somehow there is still some sort of relationship that gives these fracture patterns. And the next thing we want to do is change the ice thickness and see if there is some kind of characteristic size relationship between these ice blocks size and the ice thickness. And maybe we'll find something interesting there, or maybe it's just a chaotic process. We don't know, right? The takeaway from this is, crevasses form at fixed lateral margins first, and then they have these curved fractures near the terminus. But if you change this boundary condition to free slip, then you get these polygonal crevasse patterns. And we would like to maybe work with observational further understanding this type of behavior, and if it's this model needs improvements, and to make more sense of the map, right? And to conclude this part, I have two answers that for my two questions there. Can hydrofracture lead to full depth? Yes. Seawater level is low, and you have water in the crevasses, then you would get these fractures. But if your glacier is near flotation, then there is enough compressive stress from the ocean that even if you filled it with water, you would not get fractures. So that means you can have standing water if there is enough back stress, right? So that's fairly well known, I would say, from LEFM, but it's good to see that our model also gives the same result. And then with crevasse spacing is where we get these interesting results in 2D and 3D that show that you have crack shielding, you have crack coalescence, and you get these polygonal patterns and curved fractures depending on how the boundary conditions are. Okay, so now moving on to the next bit, we change from a phase field approach to a cohesive zone model approach. And we do that precisely because phase field is not yet fully developed to handle fluid flow. So in our previous model, we have standing water. So we assume that fracture propagates, some more water goes in, there's no flow, it's quasi-statically, the water level is changing. But if you take a supraglacial lake, and let me go to how it looks from a satellite image, that's probably, I don't know, a few snapshots spread over maybe a couple of days or so. You have very big lakes that are 1 to 2 kilometer in surface diameter, and suddenly they drain in a matter of hours to days, and all that water must go through smaller crevasses that would be able to sustain that kind of flow rates only if the flow was turbulent, right? And so in this case, it really becomes important that you do flow and fracture. And what we wanted to study is whether the rheology of ice does make a difference to how these ice fractures propagate. And so specifically, is it an elastic process or is it viscoelastic? And then can we learn something from the surface elevation data and validate our model with the observations, right? So this is where I wanted to work with computational models that can have some validation with observations to the extent possible. So we set up a model, and in the 3D idealized case, the lake is some kind of non-uniform body, and then the fractures are these parabolic crack interfaces, and we couldn't do all that, so we idealized it to a 2D plane strain case, and we only look at the 2D, one 2D slice of the plane, but we still incorporate frictional heating, turbulent flow, freezing, and heat transfer, through conduction, all that in using very simple assumptions like thermal equilibrium and 1D heat transfer in the horizontal direction and so forth. So all this work was published last year in this paper in the Cryosphere, which was selected as the EGU editor's highlight. So kudos to Tim Hockman, who's at Oxford, for setting it up so well. And the governing equations are kind of scary, but I'll try to just give the big picture. So let's say you have the entire glacier, right? So this is 4 kilometers, let's say wide, 1 kilometer thick, kind of representative of that location in Greenland that we were looking at. And the fracture is very thin, so it doesn't make sense to use phase field because it's so thin as a fracture. We use interface elements, which Pavana, you use a lot in your modeling. So we borrowed it from the composites literature and applied it to ice here. And within the fracture, there is fluid flow. But what we do is we do a global finite element based model where this is an interface, and all the fluid flow equations are solved as nonlinear algebraic equations at integration points. If that makes sense. That way we actually don't use finite elements for the fluid flow part. We just solve it as some nonlinear algebraic system at each point, and then that's why we call it the 2-scale model, where it's the glacier scale and then the fracture scale. Here we have momentum balance, stress strain, mass balance for the fluid, all that set up. But then at the fracture scale, we have the relationship that as the crack is opening up, it also can open up because of deformation and also because of melting. Right? So 2 processes dictate how wide the fractures are. And then the fluid flow, the flow rate, which goes into the mass balance, is given in terms of the pressure, which also goes into this. And there is a relationship that you solve at each integration point. And then the temperature is a semi-analytical equation where we say that the ice is only advecting heat from this liquid column in the horizontal direction. That means there is no vertical gradients in temperature. And that lets us take the simple analytical equation and relate it to the melting and also the flow, the fluid in there. Because we have melting produces fluid and freezing takes the fluid out and then closes up the crack, right? So that means that the edge melt that goes into the fracture aperture and the pressure that goes into the flow must be connected to the thermal problem. So it's a very comprehensive model. And then we have fracture using this cohesive law, where what it's telling is that the opening stress is related to, the opening displacement is related to the stress in the surrounding material. Right? So detailed model, sorry that took so long, and then we have to mesh it with the finite element. And so anywhere we have the main fracture, we have to kind of mesh it appropriately. And then this is the basal interface where we also have fracture elements, interface elements. So there also it's meshed. And then this adaptive refinement saves us some computation cost. The ice thickness is motivated from the site where we had GPS measurements through this paper by Das et al. From 2008. It was a highly cited science paper that showed very rapid drainage of a supraglacial lake. And we made some assumptions based on the lake area that was provided, which was 5.6 kilometers square. So we took some width and length of the domain, and we correspondingly took mesh size and all. So we can talk about the details later if you are interested. So we set this up. Then we looked into the literature. We found some variation of the tensile strength of ice with the temperature gradients. So we looked at borehole data from some borehole close by to that site. And what we found out is that the temperature varies non-monotonically. That means on the top, it's like negative, where is it? I think this is Y. And what you have is the basal temperature is 0. It's very close to maybe pressure melting, I don't know why. And then internally it goes to -10, and on the surface again, it's kind of -4, -5. I don't know how, but that's how it came out to be. And then we took the viscosity coefficient based on the temperature using the Lenz's law, and then also the tensile strength varies this way based on this equation. And we put all that into the simulation. So let me play these different cases, and I'll try to make an argument as to how linear elastic and viscoelastic are set up. So if you look at linear elasticity, the crack is growing, the time scale is in hundreds of seconds, so very fast propagation, and the crack reaches the base. The fluid is pushing the walls, and so your crack width is increasing. And then at some point there is enough pressure at the base for the ice to get lifted up at these corners, and then as soon as it's lifted up, it closes back down, and you see the surface deformation changing, and this is all magnified by 1000x to show these changes. And what you have is because of the bending that the water pressure creates, because it's a triangular load that applied on the surface, that bending, and till you wrote a paper on how bending changes the deformation profile, that exactly happens in here and closes the crack. And so if you just look at linear elasticity, you don't get the blister formation, which is actually seen in the field, where with the rheology of ice, where it's viscoelastic, you get much wider cracks, you get much more fluid flow volumes, and then if I go back a little bit here, you'll see that the widening continues, and then it goes underneath the ice, lifts up the ice, and then you form this blister, right? And now you can take surface points from the center line of the fracture, right? You can measure what is the uplift of that surface, and perhaps compare that with observations of a glacier height change, right? But the takeaway here is that only when you consider this viscoelastic rheology, that's when we get these under ice subglacial cracks, and we don't see it if it's linear elastic because of the bend. So quickly to wrap this up, so yes, viscoelastic rheology affected how water flow, the drainage rate into the fracture, and also this blister formation. And the hydraulic pressure in the melt water is the one that lifts up the crack. And for some reason, I think I removed that observational piece. Excuse me, I'll show it maybe at the end of the simulation. Sorry, end of this presentation. And we do see good matching with the surface elevation. Okay, so maybe in the next 5 minutes, I'll try to close on this third piece. And so here it's rift propagation in shallow ice shelves. And so we are trying to understand why large icebergs calve in the way they do in tabular manner, and how does the influence, how does the melange and seawater pressure in these big rifts influence rift propagation? So those were the two questions related to Antarctic ice sheet stability we started with. And previously, starting in my postdoc and then later as an assistant professor, we did a lot of work on these crevasses and so forth. And that was all like, full Stokes 2D. But what we wanted to test in this work is, can that same damage law, if we depth integrated it, can it work in shallow shelf formulations? So that was sort of our idea. And this was proposed by Alex Huth, who was a PhD student, who was working closely, and also eventually I think he worked as a colleague with Till at GFDL in Princeton. And the way he envisioned it is, let's take the shallow shelf approximation, or even something else like a DEVA, the depth integrated velocity approximation, and you get these ice shelf velocities. And if it is in the shallow shelves, we can say that the velocity is, because it's plug flow, it's not varying in the vertical direction, right? And the strain rates are constant, the longitudinal strain rate. And you can get this velocity, then compute the deviatoric stress, add hydraulic pressure through some approximated solutions for shallow shelf approximation. Then you apply our creep damage model, which all those previous simulations showed. And then you can figure out in that depth how much is the ice fractured, and then you depth integrate it, put it back into the viscosity, and you solve this at for many time steps. So that way you can couple a shallow shelf with sort of a in a quasi 3D manner with these crevasse propagation models. And again, just for credibility, I have to show this. I don't have time to go over all these, so I'll skip that. It came out in 2 papers, part 1 and part 2, so if you're interested, I'm happy to chat more on that. And then we had to do a little bit of pre-initialization, pre-setup through initialization, and so we used a lot of information for Larsen C ice shelf through the NASA Measures project for velocity. We got the ice shelf thickness, and as you can see, the ice shelf thickness is much thicker at the grounding line, and it becomes very thin near once it becomes floating. And then the velocity gives us the rheology coefficient, which is the viscosity coefficient. And so we do all that inversion, and predominantly what we see is this, very small regions at this point and this point here, which I marked with those poles, where the velocity goes to 0. And only when you have those as pinning points, that's when you get the velocity to match with the observed velocity in your inversion process. So what that told us is that if you don't consider those Gibbs and Borden ice rises as pinning points, you just don't get any reasonable velocity or viscosity, and you will never get the kind of cracks that we see in reality. So in fact, all rifting, maybe, if I have to be a little bit controversial, all rifting must be driven by position of these ice rises. And so Doug Ben has a new paper on that one, and where he calls them position-based calving laws, not stress-based calving laws or rate-based calving laws, right? So you need to really look into what are the boundary conditions for then answering the calving questions. So then we do inversion, we extract damage and enhancement and viscosity. Again, sorry for the interest of time, I'm skipping this. This got published in Journal of Glaciology, and here is the result that Alex and we are all very proud of. And so this is the initial case when we started, 2014, when the crack was a little bit long, but then eventually it calved this way, and our simulation target was to capture this exact iceberg fracture path, right? And looks simple that, maybe you would question me that maybe the problem is too simple. You set it up so that it couldn't have failed. And so I'll show you how you can fail. And that involves making an assumption that this crack is an open crack and there is no melange in there. When I showed the one that actually worked, there we account for the fact that there is melange, and you know how the bending and the water pressure causes the crack closure that drives this hydraulic fracture. We parameterize that through some mechanism here. And so if I assume that melange is weak and ignore seawater pressure, which is the wrong way to set it up, I would get only an iceberg which looks like that, not reality. Whereas if I include melange or include the seawater pressure, then I get, in fact, the right kind of icebergs that were observed in reality, and then we can also tune these time with some kind of damage parameterization, right? So that was the main crux of this paper, that you need to really consider how the rifts are, and not just take them as open cracks. You have to consider that there is seawater pressure in them. When once they open up, water goes in from below, and that there can also be melange that refreezes and gives some strength of for the fracture in there. Right? So okay. So with that, I answered those two questions again. The crack path curves relative to the location of ice rises. That's why they take these curved paths. And then the melange and seawater do influence the rate of propagation and also the size of the iceberg. Right? So we have to get these things right. So finally, conclusion. I showed you a polar damage phase field model that takes care of water crevasses and water-filled crevasses. It shows crack shielding. Then the two-phase flow fracture model for hydraulic fracture couples the Greenland case, and then the shallow shelf also shows good promise that we can now begin to study a lot of different ice shelves and understand maybe where and why, how the pinning points affect calving in those regions, right? And then we want to then do a multi-scale model where we couple a large-scale Antarctic ice sheet model to our full Stokes-based crack damage models, and do that in a much more multi-scale combined fashion. Again, I don't want to take too long. We do want to take our SSA framework and replace that damage model phase field with a neural network, because AI can solve some problems neatly without having to take a lot of computational cost. And so this is a project funded through Heising-Simons Foundation, along with Alex Robel and Meghna Ranganathan, who are collaborators on this. And we were able to get, we had like 16 publications from this work in the last 3-4 years, so I couldn't fit them all in one slide, but you can probably look it up on Google Scholar. And finally, we also have a short course that we developed, so we'll be offering this online in the future. So if you are interested in Phoenix, do connect with me, and we will share all the materials with you, and I will stop there. And thank you for your attention. Sorry, I missed my target.
Thank you, Ravi, for wonderful presentation. Great. As per usual, a couple of questions from students, if we have any first. Sanjana.
Yeah, great talk. Thank you so much. I have two questions. One of them is more for clarification. So when you talk about the crevasses, the propagation of crevasses, the relationship, what's like the resolution that sort of clarifies whether or not the rift is propagating? Is the propagation sort of like continuous, or is there a spatial resolution to?
Yeah. So the length scale is 5 meters. So that means, or 10 meters in some of the simulations. That means your mesh size, the 5-element mesh size, has to be 1/4 the length scale in the region where the crack is propagating.
Okay.
So we have this adaptive framework where as the fracture is propagating, we resolve the crack tip and the elements around it, and we refine it. And then there is a time step also, not just a spatial size scale, where we first solve it, then damage progresses a little bit, and then we have to resolve the problem because it's nonlinear. So we are doing several time steps where cracks are slowly propagating in time, even though there is no real time in the phase field equation that we used. So yeah, so in the sense that we have to make sure that the mesh is small enough, and also that the time steps, the load steps are small enough so that when your new crack forms, it's going to change the stress state. So you have to go back and solve the equilibrium again. So
Okay.
you're doing that in a staggered manner.
Great, thank you.
I don't know if that answers your question.
Yeah, that sort of does, because I think I was just wondering, so as I understand it, when you say that it's not propagating, it's sort of like in a steady state, like in time. There's no-
So when it stops propagating,
Yeah,
Yeah,
like
so-
when you say that there's no propagation through this crevasses.
yeah, so it's a non-equilibrium process,
Okay.
but we are solving, because once crack keeps propagating, it's going to keep changing, it's going to drive the fracture, right?
Yeah.
But at some point when the stress state doesn't change anymore, then the damage doesn't change anymore, and then the system kind of reaches this sort of a final state.
Got it.
So you can call it a steady state fracture
Okay.
for that kind of setup, yeah.
Yeah, thank you so much.
Yeah, sure.
The second one might sort of be a night question. I'll just run through it quickly because I don't want to use
Yeah.
time. When you speak about the viscoelastic and the linear elastic thing, is that like an isolated system, and like, or is it still in contact with like the ocean, and does the compressibility sort of?
Yeah, in this one, it's not. In this
Okay.
one, it's not, because it's inland. The supraglacial lake drains happen way inland, so
Okay.
we are not considering the effect of water. It's not near the terminus. But the base of the ice is actually fixed. That means it's frozen to the bed.
Okay.
That's why, it's holding up, right? If the base was fixed, then it's ill-constrained problem. We can't, finite elements will not give you a solution. So think of an ice which is completely frozen to the bedrock, and then the water is causing a fracture, and then it's forming that blister, and it's driving a crack between the bedrock and the ice and lifting it up. So that's how it's set up. Yeah.
Okay. Thank you.
So yeah, thank you. Those are wonderful questions.
Anybody else?
Yeah.
So a question about the first part. You consider a level of water in the initial stage,
Mhm.
okay? And then as your phase field parameter changes, as it propagates, is it two-way coupled in the sense that is the water position evolving with your phase field parameter as
Yeah.
well?
Yeah. Because this is a quasi-static, we were looking at keeping the ratio constant. That means the height of the water divided by the depth of the crack. We call that HSO or DS, that ratio. We were keeping that constant. So that means every time the crack propagated, we had to add a little bit more water to keep that ratio constant, and then we got those results for various cases, right? So the water level is changing in that. But it can be set up in a different way. It's just quasi-static. We can keep the water height constant as an elevation over some reference, and keep doing it, then the pressure at the crack tip is varying. But whereas in the other case, it's the height is also changing. Yeah. But it was only for getting those non-dimensional plot really to match with the corresponding analytical solution.
I have a final quick question.
Sure, yeah.
To zoom out, you doing all this amazing work that very closely and with high fidelity resolves fracture, and it's computationally very expensive. In order to run long time scale, continental scale, climate and ice sheet simulations,
Yeah.
we need a simpler representation of these processes
Correct.
for the carving.
Yeah.
What do you think? How do you think we
Yeah,
can do that?
and so I skipped through that part here, right? And I was
Yeah.
trying to make this case that if you did a whole Antarctic simulation using SISM, the NCAR model, and you calibrated it very well, like using the initialization phase, and then once you got a good velocity match with observations on the current state, and then you just run that forward if you run it forward for 3,000 years, then you get all these ice shelves, right? And when I showed this to someone, they said, we can wait 3,000 years and find out whether that's right or not. But we may not have that much time, at least us on this planet, and we get these protruding ice shelves that are not realistic as per today's state, right? So then there is a need for us to do better than existing calving laws, which are empirical. And the original idea was that you use maybe a 4 kilometer by 4 kilometer grid size, a rectangular grid on this, and then you can take that subgrid scale, and within that subgrid scale, you can do a full Stokes type simulation. So it's sort of like, taking from the atmospheric community, the subgrid modeling and terms. But imagine if your subgrid calculation takes, even on the fastest computer, a day. You don't want to run one time step of the large model and then wait a day to then run the second time step for the large model, right? You want something faster. So that's where our idea of this neural calving ice sheet model comes from, where instead of running this phase field here, we train a neural network model where the input is the stress field at various boundary points, and then it gives you directly what the crevasse depth is. That means we are highly, condensing all this very nice crack in patterns and all that we can get from phase field. We're extracting just one thing, which is some kind of a viscosity contribution that goes back into the shallow shell, right? So either the crevasse depth would be one way of extracting that information, or we can get like an apparent viscosity for that domain with fractures and put it back into the large scale model and keep running this. And with a neural network model, maybe this could be made to be minutes or less, maybe, right? So that's the aim that we're going for, but we don't know if we'll get there in the next 2 years.
Great.
Yeah.
All right.